So the central limit theorem. One downfall to collecting statistics and all the work that we've been doing is a lot of data isn't normal. A lot of data is not normally distributed, so a lot of the basic ideas, the bell curve thing, we can't just use that straight out. So what happens if we're sampling from a population that isn't normal? And what ends up happening is that as the sample size increases, the distribution of sample means changes its shape. What happens is it starts to look less like the population and more like the normal distribution. When the sample's large enough, the distribution of sample means is very close to normal, no matter what shape we started with, as long as our population has a finite standard deviation. So let's go back to our rice deal here. Let's look at a skewed population. So here we are. If I just collect sample size of 2, our sampling distribution is still skewed to the right. If I sample size 5 and sample size 25 and collect 100,000 samples, look at what happened. Just by increasing my sample size to 5 here, I'm getting closer to normal, and with a sample size of 25, it's remarkably normal. And it doesn't even need to be skewed. I can do some very, very bizarre distribution here. Right there, there's my distribution. That is definitely not normal. Sample size of 2, sample size of 25, watch what happens. This sample size of 2 sort of looks more like the population, but as we hit the sample size of 25, look at how much that resembles a normal distribution. This is how we can sample means and deal with our normal distribution skills. So, let's make a generalization. If we draw a simple random sample of size n from any population with mean mu and a finite standard deviation sigma, the central limit theorem says that when n is large, the sampling distribution of x bar is approximately normal. And how large a sample size is needed for the sampling distribution to be normal depends on how the population distribution looked. More observations are required the further from normal our population is. So here's one of these goofy looking ones I just showed you on live on the web, but as n increases, there's n equals 2, there's n equals 5, there's n equals 10, there's n equals 25, and it's been statistically found, it's been found by mathematicians that this will always happen, no matter how we start with this. If you don't believe me, go to that Rice website and try to design a population that doesn't get close to normal as the sample size increases. But what's been found is that our population will be approximately normal in most cases. Be careful here, it's not all cases, but in most cases, if n is greater than or equal to 30. So if our sample size is greater than or equal to 30, will pretty much always be approximately normal. And that's cool. I think that's amazing that this happens every single time, no matter what kind of population you started with. So here we go, servicing air conditioners. It's an exciting job, I know. Based on service records from last year, the time that a technician requires to complete maintenance on an air conditioner, it's very important here in Florida, follows a distribution that is strongly right skewed, and whose most likely outcomes are close to 0. So most of the time, this is saying that it requires very little time to service an air conditioner, and sometimes, but very rarely, it takes significantly more than 1 hour. The mean is 1 and the standard deviation is 1. So I own an air conditioning company, And I'm going to service a simple random sample of 70 air conditioners. I've budgeted 1.1 hours per unit. Will this be enough? So we have our 10% condition, because if we take 10 times 70, our sample size, we get 700. And, you know, just in the local area here in Florida, there definitely are more than 700 air conditioners in our population. So the sampling distribution of the mean time spent has a mean of our samples is 1, and our standard deviation of our sample means is 1 divided by square root of 70, or 0.12. The sampling distribution of the mean time spent is approximately normal, with a mean of 1 and a standard deviation of 0.12, since our sample size of 70 is greater than or equal to 30. We saw that no matter how this started out, if our sample is greater than 30, we will be approximately normal. So what do? We deal with our normal curve. We're looking for greater than 1.1. We need to find the probability that the mean is greater than 1.1. Our z-score, table A or calculator, we get 0.2033. If we budgeted 1.1 hours per unit, there's a 20% chance the technicians will not complete the work within the budgeted time. This shaded in area right here, greater than 1.1, that's the percentage where they are not completing their work in the allotted time. So there we go. Here's a summary of what we've just talked about. I hope that you find this as amazing as I do, that as our sample size gets bigger, our sampling distributions of means always will turn towards a normal distribution. And that is where I shall leave you. I hope you have a wonderful day.